So I think we should move on to the next speaker today.
Okay, hello to everyone. Okay, can you see my talk, Antonio?
No, not yet.
Not yet. What happened?
So you were sharing a minute,
yeah,
half a minute ago.
Okay, I will try again.
Сереж, привет.
Привет, Сергей. It's better?
Oh, yes, yes.
Okay, perfect.
Oh, that's perfect. So it's my pleasure to introduce Sergey Gavrilyuk from Marseille Université, and he will tell us about hyperbolic approximation of inertia-type dispersive models. So Sergey, we'll look forward.
Okay, Antonio, thank you very much. Hello, everyone. So I changed a little bit the title of my talk. I added this strange word, inertia type. I will explain it later. Okay, first of all, thanks to the organizers for inviting me. It's a pleasure to be even virtually in Cambridge. And finally, I would like to thank my collaborators, Sarah Busta, Mikhail Dumbser, Cipriano Escalante, Nicolas Favry, Henri Guen, Boniface Nkonga, Kim Shu, Sergei Tkachenko, and Lev Truskinovsky. Okay, I have to explain first this strange word, inertia type dispersion. Okay, for physicists, think just about champagne or sparkling water or any soda beverages, because the model describing, roughly speaking, bubbly fluids, it is exactly fluids of inertia type. But to be more or less rigorous, okay, if you want to find the equations, you have to consider as usually Hamilton's action, okay, time integral, space integral, and you have the Lagrangian. And the Lagrangian has the following structure. So you have this kinetic energy, rho v squared over 2, rho is the density, v is the velocity field, minus potential depending on the density and the material derivative of the density. So material derivative rho dot is d rho over dt plus v gradient rho. So we have to find Newton law from this Hamilton section under the following constraint, conservation of the mass, as usually. And then you obtain the governing equations. So you have mass conservation law, and finally, sort of strange fluid. It is a fluid because the stress tensor is spherical. P multiplied by E is unit tensor. And the pressure is not classical Legendre transform of the energy as in the case of W function of rho, but it is variational Legendre transform. So delta over delta rho is classical variational derivative. Okay, so this is sort of fluid I will consider. But now we have had previous talk. Okay, in previous talk, we talked about surface gravity waves, dispersive surface gravity waves. So think better about surface gravity waves, because formally fluids with inertia or surface gravity waves is exactly the same, mathematically speaking. So if you consider shallow approximation of Euler equation with a small parameter h over L, where h is typical water depth and L is a typical wavelength, then you obtain classical Serre Green Naghdi equations, okay, where it is formally exactly fluid with of inertia type. Potential W is given in explicit form, so it is sort of energy related with the gravity, gh squared over 2 minus h dot squared over 6, plus you add constant to have well-defined Hamilton's action. And the equation of Serre Green Naghdi equations, sometimes people use words nonlinear Boussinesq system, is exactly what I wrote before. Instead of rho, you put h here, and you have equations sort of conservation of the mass, where v average is just depth average velocity. And p is given in very simple form. When the red terms are absent, you have just classical seminal equations, and with these red terms, you have what people call Serre Green Naghdi equations. And if it is a little bit complicated for you, okay, no problem. You think just about very simple toy model, the BBM equation, so Benjamin Bonner-Mahoney equation, and this equation is just Hopf equation, and you added sort of inertia term. So inertia, roughly speaking, means you have conservation laws, okay, and the momentum equation contains time-dependent derivatives, okay. Okay, for BBM equation, you can always also find the Lagrangian, and it was done by Peter Olber in 1980. So Lagrangian is a little complicated. You have to introduce first the potential phi, and u is phi x, okay? The Lagrangian is given in this form, and you have also Hamiltonian formulation. For this, you have to invert this positive definite operator, 1 minus d squared to dx squared. So they like a little bit BBM equation and S-GAN system. They share the following common features indeed. So everyone can plot the phase and group velocity for Serre Green Naghdi equations or for the BBM equations, and you see they're exactly the same. And what is important is that the phase and group velocities are bounded. Okay, the equations are almost hyperbolic. They're non-local because fluxes depend on time, but they're almost hyperbolic in the sense that the velocity is finite. Okay, it's bounded. Both equations admit, both systems, S-GAN system and the BBM equation admit a variational formulation. And finally, for both equations, you can find non-local Hamiltonian formulation. For example, for Serre Green Naghdi equations, it was done by E. Lee. And for the BBM equations, I already mentioned by Peter Olber. And what is interesting is the following fact: they admit discontinuous solutions. Okay, this is a little strange, but I think the first time it was remarked by Gennady L., Mark Hofer, and Michael Scherer. They constructed for the BBM equation the following discontinuous solution. Like you take on the left constant capital U, U is positive, okay, and on the right minus U. Then the Rentgen-Hugoniot conditions for the Hopf equation gives us stationary shock at x situated at x is equal to 0, and this is formally weak solution to the BBM equation. However, these solutions are unstable under small perturbations, what is shown by Tibor Congy, Gennady L., Mark Hofer, and all this Michael Scherer. They also studied expansion shocks when you change the signs of U, okay, then formally a finite time, you have always these discontinuous solutions degenerating after that into a rarefaction wave. And rarefaction wave is also a weak solution. Okay, what is strange and what is very perturbing, the fact that you have, even if the structures are transient, so they dissipate in finite time, I mean the expansion shocks, for example, and when you have real shock, it is unstable. It is very troubling to have discontinuous solutions for dispersive equations. And finally, what we discovered recently, both for the BBM equations and also for the Serre Green Naghdi equations, discontinuous solutions, traveling wave discontinuous solutions, which are stable under small perturbations. How to construct this solution? Consider, for example, the BBM equation. So you can find periodic solution depending on 3 parameters: wave velocity, velocity of this periodic wave train, the wavelength, and the amplitude. Then, okay, I can find a constant state, denoted here U star, okay, such that this combination U star, cold state, and hot state correspond to the periodic solutions can be related by generalized Rentgen-Hugoniot relations. So this structure is a stable discontinuous solution. but we have to understand what does it mean, discontinuous solution, because, okay, what is the definition of such a solution? Okay, first of all, there is a condition for existence of such a structure. This is an obvious condition. So the shock velocity should be equal to the velocity of the wave train, okay? Then, I will explain this later, we have to satisfy the Rankine-Hugoniot relations, okay? What are the Rankine-Hugoniot relations? You take for the BBM equation classical jump conditions, even if you have here second derivative. The fact that you have the velocity of the shock coinciding with the velocity of the wave train, you have the same value of d here. But you have to add some extra condition coming from the calculus of variations. Okay, we'll show this later. Okay, and we can say we can construct exactly this solution. This is just formal. Okay, so there's no study about stability of such solution, but formally it verifies Rankine-Hugoniot relations and also this strange condition that the derivative on the left and on the right should be 0. What is interesting, if you consider Wisdom system for the BBM equation, and you consider just the first equation, and you write shock relation for the first conservation law average on the periodic solution, you obtain minus du bar plus u squared bar over 2 is equal to 0. Consider this Rankine-Hugoniot relation for the Wisdom system. And this relation is a consequence of this, okay? So roughly speaking, it follows directly, it is equivalent to this first relation. Okay, this is also troubling because, okay, you have now something which is discontinuous for exact equation. You have shocks of the Wisdom system, and this situation was also studied, shocks of the Wisdom in the Wisdom system by Sprenger and Mark Hofer, okay, for the fifth order Cattaneo equation. But the big difference between, for example, BBM system and Serre Green Naghdi system and the fifth order Cattaneo system, in the last case, you have this heterogenic orbits connecting periodic solutions. Okay, this is why you can understand when, okay, for Wisdom system, you can have analog of this periodic orbit, so you can have shocks in the Wisdom system. While this situation is more delicate in the sense you're talking about shocks of original, the BBM system, and exactly the same thing can be constructed for the SGN equations. Now, what is a strange additional condition why I use the words generalized Rankine-Hugoniot condition? It's a very simple thing. It is called in the calculus of variations Weierstrass-Erdmann condition or Kone condition or broken extremal condition, if you want. Just not to speak too much about this, consider a very simple physical example. Imagine you have a heavy string fixed at point A and point B, and then you put a mass point which can slide over this heavy string. And then finally, the optimal configuration, okay, coming from the solution of the following variational problem, you have to find the minimum of the energy of this heavy string. G is gravity, gamma is the linear density, and y of s is just the graph of this heavy string. And then you add potential energy of the mass point. So you have to find the form y of s of this curve and also the position C where you have these mass points. And when you solve this problem, okay, it's a problem for textbooks, you obtain finally, you have two classical, okay, solution is not, of course, C2, so you have piecewise smooth solution. Each part is catenary curve, okay, and then this extra condition tau plus E is equal to tau minus E, where tau plus and tau minus are tangent vector in this point C, such that these angles are the same. This extra condition. This is exactly what we obtained, okay, by saying we have generalized Rankine-Hugoniot relations. So in this sense, it is weak solution. Now, can we realize this solution numerically? Yes. Finally, it's very simple. Take, for example, a periodic wave train, okay, surrounded by constant states. Okay, for simplicity, we took these constant states, which are equal to the average value of a period. Okay, and then what happens? You solve the Cauchy problem. Okay, and what happens after some time? It appears a constant cold state, constant region, and this part of the wave train is not perturbed at all. Of course, because you solve numerically this problem, you have a just dispersive shock wave flowing to the right, and you have another stuff, okay, another dispersive wave. But here, this constant state is formed naturally. And this is exactly when you check, when you the relation I showed before, Röntgen-Hugoniot relations, they are satisfied completely. This shock links this constant state with the maximum of the periodic wave train. Of course, if you have now just infinite region filled with periodic waves, you obtain just stable traveling wave solution with this strange shock inside. Okay, now we saw, okay, the same stuff, the same solution can be found also for the Serre Green Naghdi equations. And finally, if you want to solve this problem, what you should do, okay, you rewrite, for example, the BBB equation in such a form, you introduce the variable k, u minus uxx, and you write the BBB equation in such a form. And now, at each time step, you have to find k first, and then to invert this positive definite operator to find u. So this is very expensive procedure. Okay, the same exactly can be done for the Serre Green Naghdi equations. And also we saw that we can have discontinuous solutions. We have to treat it naturally, okay, without saying, okay, in this place we have a discontinuity, what to do, and so on. And also, you want to solve the Cauchy problem with discontinuous initial data, okay? So if you want to solve what people call actually Gurevich-Pitayevsky problem, you have a step function initially, and then you will see how the dispersive shock waves are formed. You need to work with discontinuous solutions, discontinuous initial data. And of course, it would be better to have, instead of dispersive equations, hyperbolic equations. But in our head, hyperbolic equations are always associated with earlier equations of compressible fluids. And okay, textbook case, you have just a dam break problem for the seminal equations, okay? You have classical shock propagating to the right, and the reflection wave propagating to the left. Okay, so it's nothing to do with dispersion, because when you add this dispersion, you have completely different picture, okay? And this is almost a textbook case after the work of Gennady, Roger Grimshaw, and Noel Smiles, okay? And I took here the height ratio 1.8 exactly as they did, okay? So it's nothing to do, it's completely different solutions. However, people thought about this before, especially for parabolic equations. If you have a heat equation, okay, Tt is equal to Txx, we can hyperbolize this equation, and Cattaneo was first to propose this approach, just to say, okay, I have to introduce additional variable q, and to write relaxation equation for q, such that when time goes to infinity, q becomes Tx, okay, relaxation time is very small here, and actually people developed such an approach, Cattaneo-type approach, for Navier-Stokes equations. Now we have actually hyperbolic Navier-Stokes equations, and then such an approach was also applied for dispersive equations. Formally it works, okay. However, new idea I want to present here, we already understood that we have what people call conservative systems, okay. We have Lagrangian, Hamiltonian systems and so on. So if you want to have relaxed system also Lagrangian type, you have to perturb only the Lagrangian to conserve the structure of the governing equations, what I'm going to present. Okay, so this is finally the plan of my talk, because it was a very long introduction. Okay, for the family, okay, for this physical objects, dispersive systems with inertia type, I want to introduce to find at least one parameter family of augmented Lagrangians. Okay, and when this parameter goes to plus infinity or 0, we should find the original Lagrangian. And the following fact is very important. The Euler-Lagrange equation for the augmented Lagrangian should be unconditionally hyperbolic, because I want to apply standard methods like Godunov-type methods and so on to work with dispersive equations. And finally, this is a little bit strange. Maybe people who studied hyperbolic equations, okay, know this, of course. The so-called subcharacteristic condition or wavesin condition, when you have original system, hyperbolic system, and then you have relaxed system, you should have some relations between characteristics of the relaxed system and original system. And here we have to formulate a new condition because we have here dispersive system, and finally it is a sort of wavesin type condition. The phase velocities of waves correspond to the master Lagrangian, so original Lagrangian, should be interplaced between the phase velocities corresponding to the augmented Lagrangian for any wave numbers. Okay, this is a little bit strange, but very important. Finally, how to proceed? Okay, just this is a master Lagrangian for the BBM equation. And then instead of one potential phi, I will introduce three potentials: phi, psi, and phi. C is any positive constant. When I look for Euler-Lagrange equation for this augmented Lagrangians, I obtain the system of three equations. When the parameter C goes to, so unknowns are U, V, and W. When the parameter C goes to plus infinity, W becomes UX, and V is minus WT, and we recover the BBM equation. Very nice system, because it can be written as symmetric T hyperbolic in the sense of Friedrich's system, can be written in terms of Riemann invariants. Two eigenfields are generally nonlinear in the sense of Lux, so it's the third one, we see it immediately is linear degenerate. So we are happy with this because it's classical standard hyperbolic system. Okay, and also what is interesting, it admits exactly three conservation laws as original system. Older also proves this, that the BBM equation admits only three local conservation laws. The same happens here. Now we want just to understand if the system is better than BBM equation. Okay, for example, we repeated here the computations, okay, given for the BBM equation and for hyperbolic BBM equation. It gives exactly the same result. However, here you can see, okay, it's a little bit thicker, but indeed it's just bad scale, because if you count here the number of periodic waves which are not perturbed, it is 18, and exactly 18 here. Just sorry for bad pictures. Okay. Okay. Now we can compare also original equations, BBM equation, with this hyperbolic system. Okay. For this, we have to find a solitary limit of the wavesin system for the BBM equation. It's completely awful expression, but it is exact limit. And now this technique becomes very, okay, it's almost exercise in textbooks, because after works of Spenger, Hofer, L, and also, I don't know, van der Sande, maybe I pronounced well, okay, also Gennady, Mark, and This algorithm is also explained very well in the paper of Sylvie Vincent-Gavage and Miguel Rodriguez with Mietka. Roughly speaking, you just take Hamilton's just wave action equation and pass in the limit in this equation instead of to pass to the limit in equation for the wave phase, which becomes completely degenerate. And then you can find Riemann invariance for this system, also in explicit form, and you can compare the hyperbolic system and this limit asymptotic solution on some simple problems like interaction of a solitary wave with a rarefaction wave. You have an incoming solitary wave of a given amplitude, and you want to know what is the amplitude of this solitary wave after passage of this rarefaction wave. And red is analytical solution, analytical value, and numerical value is exactly the same. So this is a good approach for the BBM equation. Finally, exactly the same technique can be developed for nonlinear Wavesin equation for the Serre Green Naghdi equations. The Lagrangian is given, okay. When you write the Gaussian equations, it is just a P system, okay, where the pressure is expressed, okay, we'll show it later, as a variational derivative. And then the augmented Lagrangian is also very simple. You have just to add this penalty term. Tau here is 1 over h, okay, and it is a new variable. So when lambda goes to plus infinity, eta will be like h, so this term is negligible, and eta t will be ht, and you recover original Lagrangian for the Serre Green Naghdi equations. So it should work, okay? This is a master system, obtain Serre Green Naghdi equations written in the mass Lagrangian coordinates, and you will see here classical P system people know very well for Euler equations. But now P is not just a derivative of the energy with respect to specific volume tau, but a variational derivative. For the augmented system, you have the same P system, but with a different definition of pressure, and also because you introduce new variable eta, you have extra equations. And this system is also hyperbolic. So you have linear degenerate field and two fields which are generally nonlinear in the sense of flux. So you can apply this thing, and it works very well. And before it was just asymptotic method, okay? So, and finally Vincent Duchesne proved, he justified this method, okay? So he proved that the solution of the approximate hyperbolic system are close to solution of the original Serre Green Naghdi equations. And the second thing what we did, we extend our system, we introduce more variables. So we need to know how to put initial condition for new variables. And also when some justified it and propose some procedure to do this. So actually we can go further. Okay, 1D problem is just to begin. And now we are able also to solve multi-D problem. Here is a dam break problem where the initial region is just a square, okay? And then after some time, this picture appears, okay? So we see this. You have a system of dispersive waves. You can see it clearly. And inside, very funny picture formed for the square region. Okay, so it works very well. The time of computations is quite rapid. Okay, it works. Now let us consider more serious problem, 3D problem. Okay, with bottom topography. This is a recent work with Sarah Busta, Pierre Escalante, Michael Dumbser, Nicolas Favry. The Lagrangian can be written also not immediately, but it can be done. So V bar is always average depth average velocity. B of x is the bottom topography, and this is a Lagrangian for the Serre Green Naghdi equations in multi-decays over topography. Okay. Now, how to introduce the augmented Lagrangian? Okay, you add just this penalty term. You introduce new variable eta. Okay, when lambda goes to plus infinity, eta goes to h, and you should do something. Okay, you have to replace h dot by eta dot. Now, it is a little complicated, and we can consider what people called mild bottom approximation. So I will neglect the squared b dot here, but I will keep squared b dot in this term because mathematically it's much more interesting. So we keep here linear term, of course, but also we'll keep here 3 over 2 b dots. Okay. So I have time or not? Little. Okay, maybe I have to finish. And this computation, 3D computation, interaction of a solitary wave with an island. Okay, just last slide, almost. Okay, and okay, so it works perfectly. Computations are quite rapid, and finally, this hyperbolic approach works in three-dimensional case. Conclusion. So we propose augmented Lagrangian method for inertia type dispersion. So it could be BBM equation, SGN equations, bubbly fluids models, even 1D solid mechanics. You remember this talk of Karima, equation of state was exactly equation of fluids with inertia. Okay, the corresponding Euler-Lagrange equations are hyperbolic and approximate with a very good precision the master system. And what is important, we are able actually to work with discontinuous initial data. So this is a new method. Okay, thank you very much.
Thanks very much, Sergey, for your very interesting talk. Is there any question? Please feel free to drop a question in the chat if you want to.
I have a small question, Antonio.
Yes.
Okay, Thibaut.
Please.
Hi, Sergey. Very interesting talk. I had a small question concerning the augmented BBM equation.
Yeah.
What is the dispersion relation for the augmented BBM? Stays the same than BBM, or it changes?
Yeah, it's very close. It is a little bit different, but I didn't plot it. Okay, but it is exactly almost exactly the same. So you change the parameter c, okay, and you plot it. I can send you a paper where we did it. Okay, we studied dispersion relation for this hyperbolic BBM system and for the exact BBM equation. They're very close.
Okay. Okay, great.
This indeed, this is a possibility to make a choice of c. Okay, how to choose c, and c we choose always in this way. We compare just dispersion relation.
Okay. Okay. Thank you very much, Sergey.
Okay. Thank you.
Thibaut, any more questions? I'll probably ask one. So, I'm also curious about the augmented system. So, the augmented system you wrote, is it hyperbolic? Is it of the same type of the original system, or is it a different type?
No, it's always hyperbolic for any value of lambda. Okay, and the accuracy is capital O of 1 over lambda. Okay, when lambda goes to infinity, okay, solutions are close. Okay, more precise results can be found in the paper of Vincent Duchamp.
Thank you.
Okay.
So, okay, if there are, is there any question in the chat? I just checked the chat. If there are no more questions, I think, so I would like to thank both the speakers of this part of the session, so Rosa and Sergey, and I think any more discussions can continue into the breakout rooms.